my background is that I spent some time working in ML, and then went to Stanford for my undergrad and master's in AI, and then worked at a security company for a while, mainly working on bot intrusion and automation attack detection. So after that, then I decided to write a book on this subject because I thought that there was so much noise in security in general, and any other vertical that uses ML or claims to use ML for anything. I'm sure if you walk around the conference floors, you'll find that everyone is claiming to have some kind of AI solution, but if you just try to poke a little deeper, then you realize that it's a lot of BS. So the purpose of this book is really to try to uncover some of that and see what is really possible. So it's a technical book, there's code inside, and the book is a basis of the class that I'm teaching in Berkeley right now in a graduate program, and it's making use of data science and ML in security context. Aside that, I started a security company. I started a company last year that's funded by Google that works in the financial crime space. So we are looking for money laundering in banks and financial institutions. And we're a small team. If you're interested in finding out more and potentially joining us in SF, let me know, and then we'd love to chat. Aside from that, I spend my spare time consulting at Facebook for the Russian interference problem and the bot problem. That's where my co-authors works, and so I'm just helping out. So a lot of the context of this talk came from just conversations of people. I used to go to a lot of security conferences, a lot more than I do now, and talking to people who are just spending a lot of time looking for vulnerabilities in software, spending a lot of time looking for ways to exploit software to get the bug bounty rewards, to get any kind of recognition for finding crashes in programs. I realized that the way that people were approaching the problem of finding exploits looks very similar to how people approached antivirus, how people looked at trying to brute force a problem a decade ago, 20 years ago in security. And I realized that the only sensible way forward is for this field to be a lot more data-driven. And so I started doing some research in the field into how different data techniques have been used to improve the processes of program analysis in general, not only for finding exploits, but also just for static analysis in general, understanding how programs work, understanding the nature of code execution. So bug discovery is all about fuzzing to find crashes and vulnerabilities. Symbolic execution has become a huge thing in the past 10 years or so, particularly because there's been lots of computational improvements in solvers. And so today we'll be looking at a plethora of different kinds of approaches that have been recent works in the field, and then also looking at what potential improvements there can be as we go on in the coming years. So just so we can get a feel of the room, how many folks are kind of familiar with program analysis, with fuzzing, have done fuzzing of any sort? Okay, cool. That's good. That's great. So for those who are a little bit more unfamiliar, this is kind of a very simplistic overview of the different levels of access of information you have to a piece of software, or the ability for you to reach your hand inside a piece of software and the code execution flow or the compilation flow to interfere with how code is being executed in runtime. And in general, from left to right, you'll see that the less access you have to interfere with the way that code is being run, the less you're able to kind of use that insight to generate more intelligent ways of finding out how the software is being run, and consequently, you have less data to work off. So black box random fuzzing, kind of simple. You have only the ability to execute and observe the output. So you only see the input and output. It's just a black box. You feed in whatever you want to feed in, and then you see what comes out on the other side. It's kind of the canonical fuzzing approach. Grammar-based fuzzing leverages some knowledge that you have about the software's input schema. So if you know, for example, it's a PDF parser, then you would know that, okay, there are certain formats according to the PDF spec, which is surprisingly large, that you can shape your input so that it's considered valid input. and then you can use that as a schema for you to think about how you can tweak the input in ways that will allow you to potentially crash your software with a higher probability than not. Gray box instrumented fuzzing is, I think, becoming a lot more popular because of this one particular thing called AFL, American Fuzzy Lot, which I'm sure anyone who's looked into fuzzing would have experience working with, just because of the generalizability of this piece of software, the promise of it, and the kind of potential for it to find bugs in an interesting way, more interesting than we've seen before in other kinds of generalizable software. And it uses dynamic build time instrumentation. So during the compilation process, you can think of it as just injecting certain hooks into the code execution flow so that you can figure out what exactly is going on, and you don't just have to rely on the input and output, the start and the end. You can rely on intermediate chapters within the program execution flow so that you can actually find out what is going on at each time in the program execution runtime. And of course, the more access you have, white box fuzzing is when you have access to the source code, when you have a lot more information about whatever is going on in the piece of code you're running, and you can then use some other more enhanced approaches to figuring out how you should change your input, how you should tweak the software execution so that you can then increase your likelihood of finding crashes. So just examples of doing this, like black box random fuzzing, of course, like you can just generate random strings, generate random bytes, string them together, and then put them into your software. This is, I don't think we need to talk too much about this. Grammar-based fuzzing, there are some examples, not too many. I think GramFuzz is one of the more popular ones. And of course, instrumented fuzzing, AFL, LibFuzz, they are the most popular ones. And then constraint-based fuzzing, white box fuzzing, more popularly because of CGC. The past couple of years, Anger has been coming up a lot, Sage has been coming up a lot. So just some examples of what's going on. So the process of today's session is that we want to go through about 8 to 10 different papers, and I only spend about 1 minute on each of them. The purpose of this is not to give you kind of the complete picture of what exactly this paper is talking about, and I'm sure I'll be doing a lot of these in justice because it's kind of impossible to cover everything that the researchers did to put into a 15-page paper over the period of 1 year and then summarize it in 1 minute. But the general takeaway that I think I myself personally got, and I feel like would be valuable to share, is the trends of research and the trends of how these different snippets of time in these different pieces of research have shown that data science in general, or any kind of data-driven approaches to use in the vulnerability discovering process has been helpful, and then maybe influence future research and stuff that I've done as well. I'll talk in the end, and also stuff that I think anyone can do even if you're completely new to fuzzing. So this is stuff that's kind of old, 2010, 2011. This is like 8, 9-year-old research. But I think it's particularly interesting. When I was looking around in the field for how, in particular, how to define the starting point of when the process of fuzzing really became a data science subject instead of just staying in the realm of systems, then I think these two papers stood out. In particular, the one on the left, it's by Stefan Savage at UCSD, famous guy, and the main idea around it is the very canonical machine learning approach, which is that, hey, over the past 20 years, there's been a bunch of people that spent their entire lives pulling their hair out, looking for vulnerabilities by studying nightly releases of software, and then looking at how this different software has been changing, and then looking for bugs like this. Now, this is obviously not scalable as software becomes more complicated, as there becomes more and more of such software being used in critical systems. And so how do we scale this up? Maybe we can automate this process a little bit by looking for the patterns in previous vulnerabilities we have found, and then trying to see if we can find some patterns in them and then automatically discover them in the future. So this is the very traditional kind of machine learning approach, right? You have a bunch of data, they're by nature labeled because they're things that people have found to be suspect or vulnerable. Then you use this to find new things. Maybe it works, maybe it doesn't, but let's see. The other study is kind of a there's a white side and a black side. So this is more of a success, this is more of a failure. But then we'll see the differences in the approaches and then try to see if we can come up with some pattern. They publish very different results, even though they're basically doing the same kind of study. They are looking for vulnerability, they're predicting vulnerability and also predicting time to exploit of vulnerabilities by learning from these public exploit databases, public vulnerability databases. So the Savage paper basically used a very, very simple SVM model, support vector machines. It's taught in ML 101 classes in your freshman computer science class. And it uses a bunch of different manually generated features. So remember, this is 2010. There's a bunch of people who are all systems experts. They've spent their entire careers analyzing binaries, analyzing any ELF files, right? So they're not only using the data science approach, but they're also combining it with the expert knowledge of how likely is this feature able to help me to find a vulnerability, and then they're using that to kind of build this model. So the kinds of features that are using, hopefully you can see this, but there's a bunch of interesting stuff, there's a bunch of not so interesting stuff, but there are things that if you are a researcher looking for bugs, you would probably try to generate these yourselves anyway, maybe plot them out, maybe just look at the values of them and try to see how likely is it that this software is to be buggy given your own experience. So they use this approach. They use this manually generated 90,000+ features, and then they claim to have really good results for generating predictions. The other one claims to have very bad results for generating predictions. They use the same source of information. It's the NVD CVSS public vulnerability reports. And the thing is that there's much less talk on data validation, on cleaning. And it cites data quality actually as the main reason for the failure to predict reliably the time to exploit. So the time to exploit prediction is basically, given that you have a vulnerability being reported, and then you have exploits being reported as well, what is the time range between them? Given that in the past you have visibility over the time range when a vulnerability is reported and then when it's exploited, then maybe you can predict how likely it is that a yet to be exploited vulnerability is going to be exploited, and then you naturally have that feedback loop when you then get the exploit cycle reported. So I think there's only about a 40% success, so less than random chance. And the general takeaway of comparing just these two papers is that data quality is everything. So there tends to be a lot of, whenever I talk to folks about, okay, this is what I do, I look at different algorithms and figure out if it's good for this problem or not, and then they say, okay, so well, how do you write your machine learning algorithms? And the truth is that no one really writes new algorithms all of the time. They're just using the same few algorithms. They're using neural nets. They're just using literally the same piece of software and then just tuning parameters to make things happen. And most of the time is spent on cleaning data for a good reason, just because it matters a lot more what kind of data you're using, how you're wrangling your data, and what kind of input you're putting into these systems in order to train semi-intelligent or pseudo-intelligent systems that you think are doing automation in a less than direct way. So that is the first kind of basis that we want to set on course, which is data quality is everything. So given that all of the research in using data science for program analysis has been looked at, the only ones that kind of are valid in my mind, or the only ones that kind of make sense as a grounds of a comparison between each other and to use as a data point in this kind of 10-year trajectory is that we want to look at only research pieces that have put more thought into how they're generating their data sets, into what kind of data sources they're using. And in general, I think this has improved a lot in the last 10 years, but then early on, it wasn't the case. So let's take a step back and look at the problems to solve in fuzzing in general, right? So you have this piece of software. It doesn't matter how much access you have to it, but the main problems are that fuzzing takes too long, right? If you have a simple piece of software to fuzz, sure, you can come up with some random seeds, even if you know nothing about the program, and you can find something pretty reliably, pretty simply. But the truth is that most of these things are found by people if they're worth any money at all already. And you don't really want to find these simple cases. You want to find the interesting cases, the ones that kind of are meaningful and are not, quote unquote, trivial enough that they can be found by just someone looking at the code or just someone playing around with the program. So the main cause is test case generation, right? The entire idea around this is that you want to feed test cases into this software such that you cause some unexpected output. And then taking a step back from there, the test cases have to be generated somehow automatically, right? Because you're not the one that's generating the test cases yourself manually. Some kind of algorithm is doing that. So this is kind of coarsely named input mutation strategy, where you basically have a seed input or a set of seed inputs that you use as kind of your starter set. And then from there, you're changing this input in some ways that allow you to maximize your likelihood of finding crashes sooner rather than later. And then also, if you look at it a little bit more philosophically and zoom out into what it means to be executing a program or writing code, and each of your lines of code or each line of logic is executed, then you can actually visualize it as some kind of execution tree where each conditional clause, each kind of loop statement actually can be branched out, and you can follow that logic sequentially, imperatively. So the idea is that if you can exercise all possible routes exhaustively, then you can, with caveats, potentially find all kinds of edge cases in the software, right? And so why don't people do that? Because most non-trivial software, of course, have huge execution trees, and so you're not able to do that all of the time. And so the issue is, if you have unlimited time, of course you can enumerate over all of these cases, but that's always not the case. You don't have unlimited time, you don't have unlimited resources, so it's really getting to the crash with higher likelihood as soon as possible, as quickly as possible. And then the last thing is, the difference between exploitability and vulnerability. I don't think I'll go too deeply into this, but there's some interesting work done in this area too. So it's kind of an intimidating diagram, but the way I split up the field is that there tends to be two general classes of research. One is generative, one is predictive. And the generative ones, I think, are generally a little bit more exciting just because it allows you to action on it in some way. Generative approaches mainly mean that you are able to run the algorithm that generates some input that helps you to come up with crashed test cases a lot faster than without. So it's measurable because you can try using these test cases generated by these algorithms. You can try using test cases generated by some other implementation strategy. Then you compare the time to crash, or the time to finding a vulnerability or finding a crash, and then that's your metric. In predictive approaches, it's a little bit different. It's a little bit more indirect. So it's more of the analytical side of the problem, where you're looking for parts of the software that are more likely to contain crashes or vulnerabilities. You're looking for exploitability of a crash. You're looking for the time to exploit. And then the other side of it is a little bit more in the theoretical realm, where you're looking for how you select state when you are choosing which path to branch down into, when you switch between fuzzing and the other approach, when you are using a kind of a dual engine fuzzing methodology, which we'll look at a little later as well. So let's start with the first one, which personally was the first paper that I read in this area, which was pretty interesting. So you can actually try this software out. It's called vDiscover or VZUF, and if you run it, it actually doesn't work that well in practice, but the idea around it is interesting. So the thing is that they split this entire process of extracting features from binaries up in two steps. The first step is you want to extract static and binary features from binaries. Static and dynamic features from binaries by just imploding it in some kind of sandbox and then just analyzing static features. And then you use this to prioritize your test cases. So the main thing is that you have a bunch of test cases already generated beforehand, and you want to figure out how you can queue them up in a way that allows you to find things better. So the assumption behind this is that you have some way of already generating pretty good test cases exhaustively, and you just want to prioritize them into the ones that will likely cause you to find interesting things and not just run and die. So it used the Mayhem team symbolic executor, and then it used pretty simple models, MLP, multi-layer perceptrons, to kind of precursor to neural networks and random forest to do predictions. And it was able to find some pretty interesting test cases. And the thing around this is that they used a kind of naive way to look at the entire problem, because if you think about the process of, let's say, malware classification, this is kind of the way you would look at it, right? Because you want to look for different artifacts in a binary that allow you to classify this binary into some category. The category in a very coarse nature could be whether it's malicious or not. In a more fine-grained nature, it could be, does this binary belong to this malware family that just exhibits this kind of characteristic? But the step back from this paper is asking a deeper question, which is that, is there any kind of characteristic of input cases or software features that indicate its vulnerability, or is there even a pattern that you can kind of look for in general, such that you will know with some surety that this piece of software contains a bug? And I think the conclusion from that paper was that it is an inconclusive no. And the idea behind it is that the entire class of vulnerable software is so huge that it becomes more of an anomaly detection problem, where you're looking for classifying the unknowns and the knowns, where the unknown class is so huge and so massive that you cannot possibly come up with characteristics to classify them. And so that, I think, in general, is the conclusion of this paper, which is that it proved you cannot use such an approach to think about the problem of input test case generation. The other thing is thinking of input cases less of thinking of input cases less in a sense of randomly changing things about, but combining fuzzing with grammar-based learning. So when you look at, for example, the PDF parser case that I mentioned earlier, then you can see that there are actually certain ways you can mutate the input that can generate, more likely than not, valid PDFs or valid schemas for this particular program that you're feeding it into. And it kind of uses the kind of already old idea of sequence to sequence, which is what's being used for most natural language translation. So if you go to Google Translate today, they actually shifted from more intricately built language models to this kind of seemingly dumb approach of sequence to sequence, which is the idea that instead of trying to understand what exactly a sentence is saying and then translating this sentence from English to French, what you're doing is that you're feeding the English language version of the sentence and the French version of the sentence side by side into a model, and then you're letting the model learn that, hey, if this sentence comes first, then this is the French sentence that comes next. So that's kind of using brute force data to solve the problem, and that's in general the trend of the last 20 years, which is that there's no point investing in better algorithms when we have so much data. And improving data by 10% gets you a 10x improvement. Improving algorithms by 10% gets you a 10% improvement. So that's why everything is going this direction. But this paper is interesting because it's kind of the first meaningful approach of using neural network statistical learning to automate the traditional input generation. And it has pretty interesting results. So it was able to mutate a complex PDF file. If you think about a PDF file, right, it's actually a lot more complex in structure than most languages. And well, that may not be true. I think it's a lot more complex and difficult to get right because the criterion for getting a PDF, a sequence of bytes that constitute valid PDF, is a lot less, is a lot more sensitive to correctness and incorrectness than an English sentence. So you can generate an English sentence with an extra word in there, and people would still recognize it as an English sentence. Whereas if you had an extra random byte somewhere, then it'll be corrupted in a file. So this was able to mutate complex PDF files pretty reliably and pretty well, which led to future work in this space. So quantifying software exploitability uses some of this idea and generates a score for how exploitable a piece of software is. It uses the features generated, and it uses sequential input schemas and grammar in order to generate a priori beliefs into how likely this piece of binary is to be exploitable, and then it feeds it into the system, and it really kind of puts the idea that you can rank software by how vulnerable they are before even running them through a fuzzer, and then use this to kind of determine how much resources you want to spend on fuzzing this piece of software. So, for example, if this algorithm tells you that, hey, it's only 20% likely that you're going to find some exploit, then maybe you only spend 20% of your resources and fuzz it for a fifth of the time that you fuzz some other software that is most likely for you to find something. And then, who's heard of GANs here? Cool. Yeah. So GANs are kind of this concept of generative adversarial networks. It's the idea behind all that deepfake stuff you're seeing. It's the idea behind generating realistic images by putting two neural networks at competition with one another or at opposition with one another, where the two neural networks are basically set up with different objectives. One is set up with the objective of generating input that you can think of as counterfeit dollar bills, and the other one is set up with the objective of determining which dollar bills that the other networks generated are counterfeit. So if you think of the process of training these two networks over and over again, then you can imagine potentially that these will eventually form a self-improving loop and generate inputs, generate samples that are so realistic. And that's exactly what happened. People just threw a bunch of data at the problem, threw a bunch of GPUs at the problem, and realized that they could generate super realistic looking fake human faces and fake everything that looks exactly like what you might imagine to be non-computer generated. So this is a little bit less interesting of a problem. We're not generating deepfakes here, but this improves the performance of AFL by generating seed files based on GANs as the idea. So, maybe some kind of program analysis nerd is trying to do this instead of doing something that can actually show up in papers, newspapers. But this helps AFL exercise deeper paths and find quicker exploits compared to the default random strategy. And then we'll go a little bit into AFL later, where we want to try to dig a little bit into what AFL actually is, and then try to see if we can actually improve it using this as kind of a seed. Before we do that, there's a couple more interesting papers that I thought would be interesting to mention. This is part of Anger. This is part of the UCSB's C2C approach, where they actually developed this thing called Driller, which doesn't use any machine learning, but it's an interesting approach to think about the problem. So if you think about the problem of fuzzing, what you're actually doing is starting from the input of the program, you're trying to trace a increasingly exploding path execution tree, and you're trying to figure out how you can optimize your fuzzing approach, your fuzzing strategy, your inputs, such that you can exercise more of this tree, and then you don't have to spend more resources fuzzing, more time fuzzing. The problem is that there are some approaches that allow you to generate analytical outputs from programs a lot more reliably compared to fuzzing. So this approach called symbolic execution, basically at a very high level, tries to convert a program into an analytical problem, so that you can express the output of the program as a algebraic expression constituting of the input. And then using that, you can then use mathematical equations to solve it and solve for what kind of input will cause a discontinuity in this equation and cause some kind of crash. And the problem with that, of course, is that most large programs cannot be solved with this because it's just too computationally intensive, too analytically intensive, and the Z3 solver is one of the more popular and more successful implementations of this, but still it only manages to deal with fairly simple programs. So the idea is that maybe we can fuzz to a certain point, a certain subtree in this program, and then from that point onwards, we run some symbolic execution on that much smaller subtree in a program if we see something that could indicate that there's something very likely to be found here. And so in that case, then we don't have to potentially run the solver on the much larger global tree and can run it on a smaller set of trees, which we can then parallelize, which we can then spend much fewer resources solving for. And it actually works pretty well. So in the interest of time, let's go on a little bit. This is perhaps the paper that still has the best results for fuzzing so far, for program analysis in general. There's no machine learning, no symbolic execution, but it uses taint tracking to improve the process of program analysis, to improve the process of finding bugs. And the main idea is that most path constraints depend on only part of the input. So for example, if you look at a conditional statement like this, if s of 0 equals to x, then you abort the program. Then if your algorithm is able to, for example, detect that only a certain part of your input is relevant to exercising this code path, then maybe you should just change that. And so that's what it does exactly. It tries to look for patterns like that. It tries to look for context-sensitive branch coverage. This is a little bit of a mind twister, but it's pretty simple. So the first time the flag is set to false, and then if the flag is false, it won't abort. And then after you set the flag to true, and then the second time you run this exact same function, it actually aborts because the flag was previously set to true already. So the general idea is that most programs have some kind of global state like that, have some kind of shared state where the state can be mutated, and most fuzzers don't actually take into consideration the context in which the function is being executed. Like if you think about static analysis even, most static analyzers don't look at context when they're executing, when they're analyzing the program. They only look at the function in general, and then they look at what the current state is, what the expected state is, and don't look at changing state, because then there'll be too many variables to keep track of. But the idea behind this is that you want to look for some kind of way to keep track of branch coverage that are influenced by context, and then they're keeping track of that using a simple dictionary, and then that improves the results quite significantly. And the next idea is kind of a more ML-based approach. The entire machine learning field is based off convex optimization, which is trying to look for a optimization point, minimizing some kind of cost function by going down some gradient. And this gradient is representative of optimizing some equation computationally, non-analytically. And they're searching for input that can help them to improve the scores or improve the likelihood of finding a crash more quickly. And this improves the search process. And input length exploration. So it just improves the fuzzers working with longer inputs because they realize that the low-hanging fruit there is that most fuzzers work well looking for exploits involving short input, but then with longer input that maybe don't fit in register, for example, then it just doesn't work. So they were able to find a lot more exploits that were missed by traditional fuzzers using this approach. Okay. Now, going back to AFL, which we kind of mentioned a few times in the entire approach, I think this is the most popular generalizable fuzzer over the last 5 years or so. And it uses compile instrumentation by adding hooks into your program execution so that you can figure out what's going on at what time. You can gather some metrics on what's going on. And it uses this thing that, quote unquote, everyone kind of calls the genetic algorithm to mutate input. And the idea is kind of simple. If you think about evolution, it's a similar concept where if you change things in a certain way, or if you change certain input, if you change certain byte values, if you change certain certain artifacts about a string or a program, then it gives you a positive outcome, then you want to keep changing that, right? So maybe the program is looking for a certain byte in that location, and changing that constantly will allow you to express more code paths. So that's the simple algorithm behind it. It uses a simple feedback loop to generate a goodness of input, and then it retains input that helps to exercise new code paths. And how it knows that is by instrumentation. It knows what code paths are newly exercised and what are seen before. The great thing is that it's application agnostic. It works with very few seeds. The bad thing is that if you look at the algorithm itself, it actually still relies a lot on luck. And so this is the core algorithm for AFL. I got it from a paper that looked at AFL. And the idea around this is that basically it's a loop. It's a nested loop. You're picking an input from a queue, and then you are sampling the number of mutations in order to apply on this input. And then you apply the mutation, and then you feed this mutation this mutation, which is the candidate, into the program and see what happens, right? So you just loop through this entire thing multiple times and realize that in this general outline algorithm, there's a few things that no one really talks about. There's the pick input, which a paper that we saw previously talked about, like prioritizing input based on the likelihood of exploitability or the likelihood of expressing new code paths. And then there's a sample num mutations, basically the number of times to mutate the parent input. And this was also looked at before in the sec-to-sec paper. And you pick a mutation operator, which we'll look at in the next couple of slides, and then you apply the mutations to the site. So this probably requires a little bit of elaboration, where AFL mutates input pretty simply. This is not all of them, but this is a representative list of them. Basically, you can flip a bit, and then you get a new input. You can add a byte, add some random value to your input, and then you get a new input. And then you can override, insert, deletions, things like that, simple. And then we're just applying the concepts that we saw in the papers before and try to see if we can get better results and try to see if we can improve AFL. And so what I did was I looked at nice small data set of programs that are well analyzed and well studied. The ASCII content server in the CGC data set from a couple of years ago. And this is basically a content serving server. And so it receives commands from some interface, and then it responds with some kind of output. So the idea is that if you look at all of these, if you look at all of these different mutation strategies, you realize that some of them will work better in this context compared to others. And so if you apply a random mutation strategy selection, which is what AFL does, it just literally selects one at random, applies them to a site. Then you realize that may not be the best approach to doing that. Maybe there is a better approach to doing this. If we apply kind of human intelligence to this problem and realize that since this is a content server, the input is expected to be in some kind of schema. The input could be a little long. The input needs to start with, for example, one of those 5 prefixes that you see there: request, query, send, visualize, interact. And if not, it will just be thrown out. So maybe we want to enhance the program, enhance the input mutation selection such that it is more likely to generate those rather than just some random string. So if you look at this, bit flips randomly. That's not too promising, because flipping bits randomly will in most likely scenarios not generate valid strings that meet those criterion. But other things do. So for example, if we want to clone strings, then they come from valid inputs already, and thus are likely to generate valid ASCII input that could then be accepted by this server and could then be used to execute more code paths. So taking this as kind of the intuition for the process of improving AFL, for improving the input mutation strategy selection process, then we actually realized that we can improve the time it takes to find crashes by about 20% or so, and only requiring about 50 lines of code to patch AFL. So just some interesting stuff. I thought to also look at this other paper, which is which I thought was pretty mind-blowing when I first read about it. It's a couple of years old already, and they actually already have released some tool for you to reproduce the results in very constrained environments. But the idea is that if you can formulate a data science problem around looking for exploits, then can you formulate a similar data science problem around looking for patches to fix that bug, right? And so they went about doing this, with, I think, low expectations, because I mean, who would think that this might actually work? And the idea is that it learns from code transformation patterns, looking at other bug fixes in open source software. So you can think of, the way you're thinking about it is probably right. You look at, issues or bugs filed in open source software, and then you look at the patches or the changes, the diffs made to that line of code or the area of code such that that bug is marked as fixed. And then they use that as their data set, their labeled data set, and try to train some model that can generate these fixes automatically. And they realized that, okay, they were able to generate fixes pretty reliably. And I mean, more reliably than you would think. But correct patches for similar bugs are the same universal features across apps. If you find a SQL injection in one place, and then you learn the properties of the fix that went into fixing this SQL injection, more likely than not, it comes from a certain distribution that a model can learn, and therefore can come up with, based on the context of this new situation, select based on one of the previously seen before patches that can then fix the code with a certain reliability. And generating the correct patch that fixes both the bug and does not break other functionality of the program is a different matter altogether. So that, I think, they stated pretty explicitly in the program, but that just goes to show how much extra work we have to do in this area. And if data can be thrown at the problem to kind of do this unthinkable thing, then I think there may be a lot more that we're not imagining today that can be done in this area. So the future directions for this are, there's quite a number of them, but if you look at the cadence of the different papers, the different pieces of research that are being put out by this community, I think you can see that, first of all, enhancing data quality of any kind of vulnerability data set, any kind of bug data set is crucial, right? So any kind of reporting, any kind of tagging that we can do to any vulnerabilities that we find today can help to influence the next generation of algorithms, the next generation of research that's being put out into the field. And then the state-of-the-art fuzzing research is still kind of siloed in most systems, in most kind of systems arms of academia today, doesn't seem to use any kind of ML approach. But then there always seems to be a tick and a talk where there's a next wave of research being put out that uses ideas from those past papers and then enhances them with data techniques. And then there's a bunch of low-hanging fruit in generative methods that I realized when I started to just tweak AFL a little bit and realize that there's very simple things that you can do to push up the efficiency that doesn't require complicated systems knowledge. And then the last thing is that there's a lot of work being done in symbolic execution and taint tracking being combined with fuzzing that can be maybe and pretty intuitively improved with some kind of data techniques once we have the right data sets. So program analysis is kind of a relatively untainted field by data techniques compared to other areas in code execution analysis, in binary analysis, and what you realize is that this means that there's going to be a lot of work done, and this means that you can potentially do some work yourself too. So thanks. Hope this was a little interesting, but if you are inspired in some way, and if you feel like you wanna jump into this area, and you feel like this could be interesting to look at, then you should come talk to me. And I have a bunch of interesting stuff that I think would be good to start with, and interesting papers to read. And I think looking at this kind of plenary study of the field is always a good way to think about what's next, what you can do, and what's been done before, what you think could be done that no one else has done yet. So that's it. Thank you. Any questions? Yeah. Yeah, that's actually pretty interesting. So a lot of the field thinks of the process of classifying exploits or generating exploits using a supervised learning approach, which means that you're able to characterize both sides of the equation and you're able to come up with a data set of equal representation on both sides. And the fact is that I think as we discussed, we just touched on a little in one of the earlier papers, we saw that most bugs that are not maybe OWASP top 10 or one of those common things that you're looking for cannot actually be effectively classified using one of those approaches, right? So you're looking for something out of the ordinary, and most of the time, these are the interesting things that people are interested in looking for. You're not interested in finding some random SQL injection somewhere. But the idea is that by looking for intricacies in different kinds of input, by looking for patterns that maybe humans studying the program haven't yet realized how to generate, then there could be a potential for generating input of this nature. So I think one of the more tried and tested open source tools that is covered in this paper is the VZUF software, and I think it has consistently demonstrated its ability to find interesting bugs that that haven't yet been found even by human analyzers of the program which have studied for example like glibc for a long time. It's able to find something that approaches the problem from a different angle that a human an expert in this field would. So I think there's some potential for doing that, but still the problem space is not entirely set up for that problem to be solved very efficiently. Any other questions? Cool. So I'll be around here, but if anyone has questions about what I'm doing about this field in general, then I think it's a good time to look into it. Thank you.